So the next paper is learning to separate object sounds by watching unlabeled video. And the speaker is Ruohan Gao from University of Texas at Austin.
Thanks for the introduction. Good afternoon, everyone. I'm Ruohan Gao from UT Austin. Today, I'm very excited to share with you our work on separating object sounds by watching unlabeled video. So this is joint work with Rogerio, Feris, and my advisor, Kristen, Grauman. So let's first listen to the following audio. So this might be an audio experience that the local people here are very familiar with. Just by listening, you may already have some guesses of the events that are taking place and the objects that are making the sounds. And let's see what is exactly happening. So by showing the video, it's much easier for us to recognize the sounds in the audio, right? So the video information guides us to separate and perceive the sounds in the video. The perception of the scenes and events, like in this Oktoberfest festival gathering in Munich, is inherently multimodal. We see beer mugs, people, and the stage, and we also hear people singing and cheering and the sounds of different musical instruments. Understanding scenes and events most fully requires us to use multiple senses. We would also like to be able to make use of these simultaneous signals. Human development learning is actually also a multimodal experience. Kids can quickly amass a repertoire of objects and their sounds. Similarly, our goal is to learn a representation of what different objects sound like so that we can have a joint model of how things look and how things sound. But the challenge is that in real world, object sounds does not exist in isolation, but are usually mixed together in various scenarios. In an unlabeled video, object sounds usually exist as a single audio channel that mixes all of them together. So the problem is, how can we obtain these object sound models naturally, including from unlabeled video? So in particular, we formulated the problem as visually guided audio source separation. Given an unlabeled video, we split and pay attention to both the audio and the video frames. And the target is to split the audio into its component sounds. For example, here, given an unlabeled video with a man playing the guitar and a man playing the saxophone, we want to detect the video objects and separate the sound of the guitar and the sound of the saxophone. There's actually a long history of work on audio source separation, including some methods that also use video information to guide the separation process. But traditional approaches work at aligning strong low-level correlations between the signals, such as by detecting the onset motion of the bow of a violin. And these methods usually require clean, single audio source examples to train. And we would like to learn to separate object sounds by leveraging video objects. And we want to learn from unlabeled video with multiple audio sources. And this unlabeled video would have multiple objects making multiple sounds at once. We would like to get models for the sounds that each type of object makes. So this is our goal. And then I will show how we accomplish this and some of our results. So non-lective matrix factorization is a popular method that is often employed to perform audio source separation. Given the audio spectrogram matrix V, NMF approximates it as a product of two matrices, W and H. And W can be interpreted as long-lective audio spectral patterns, and H can be seen as activation matrix. So each column of W is referred to as a basis vector, and it captures the prototypical spectral patterns. And each row in H represents the gain of the corresponding basis vector. And a subset of basis vectors and activations could then potentially be used to reconstruct each source. So NMF can be used to analyze the audio spectrogram and extract audio basis vectors. Based on this, we set up the problem in a deep multi-instance, multi-label learning framework, and we are trying to disentangle which visual objects make which sounds. For each video, we split and obtain the audio spectrogram and the video frames. We perform NMF on its long-lective audio magnitude spectrogram to get a bag of audio basis vectors. And an ImageNet-trained ResNet is used to make video predictions to find the potential objects presented in the video. Finally, we perform multi-instance, multi-label learning to disentangle which extracted audio basis vectors go with which detected video objects. And we design a deep multi-instance, multi-label network with multi-label hinge loss to achieve our goal. And it's important to stress that the input videos for training contain multiple objects making multiple sounds. Through the MIML network, we can then discover the link from audio basis vectors to object categories. And the desired output would be a group of audio basis vectors for each object class. To achieve this, MIML disentangles sounds via visually detected objects. For example, given an unlabeled video with a guitar and a violin, we obtain its audio basis vectors. And the view information tells that among these yellow audio bases, some must belong to the guitar and some must belong to the violin. And similarly, for this video with a guitar and a piano, some of the associated red audio bases belong either to guitar or piano. And the same for this green example of cello and piano, and so on and so forth. And finally, we obtain a group of audio basis vectors for each object class. And we may never see the sound of each object class in isolation during training. MIML learns what an object sounds like by satisfying the back-level labels. Thus, we can learn which bases go with which object class by observing their various combinations. Recall that our goal is to learn class-level sounds from unlabeled video. And we have obtained per-class audio basis vectors through MIML learning. But do they really represent the corresponding object category? To better interpret what has been learned, for each object class, we get its top 100 audio bases. And we use activation matrix to combine these bases and obtain an audio spectrogram. Then we use inverse short-time Fourier transform to obtain an audio that represents the prototypical sound of each object class. And here are some examples. Note that we are generating sounds from the basis for each object class instead of from an instance. And here is the sound of a violin basis. So we can see that it sounds a lot like the pitch of the violin and the sounds of the flute and the sounds of motorcycle. So we can see it sounds like the engine sounds of motorcycle, and then the sounds of frog bases. So we can see that our MIML framework successfully learns the prototypical sounds of each object class. Then during test time, given a level video, we would like to use the discovered object sound models to guide audio source separation. Similarly, we detect the objects presenting the video frames, here the violin and piano, and we retrieve their non-audio basis vectors. And on the audio side, we obtain the audio spectrogram, and instead of directly performing unsupervised NMF and do clustering on the factorization results, we now use the learned basis to guide NMF factorization. Specifically, we initialize the audio basis matrix with the retrieved basis and only estimate the activations. And the basis vectors and the learned activation scores from NMF are finally used to separate the sound for each detected object, respectively. In the end, we obtain the separate sound for each detected object. OK, now let's see some results. So we train on over 100,000 unlabeled multi-source video clips and then separate audio for a level test video. And here is the original video. And the video predictions gives acoustic guitar and harmonica. Then let's hear the sound for acoustic guitar. You can feel the effect, right? Although it's not perfect. And then the separate sound for harmonica. Then let's hear the results of the baseline method. You can see it's a pretty difficult task. Here's another example of violin and acoustic guitar. And the separate sound for violin. And a separate sound for acoustic guitar. So our method is not limited to just instruments. Here is another example of a dog and a violin. So the dog is singing with violin. Now let's hear the dog sound. And the separate sound for violin. Okay, we also attempt to use a non-audio basis to perform audio source separation on a YouTube video with background noise. And this is our original video. We can hear laughter. And some vocal sounds in the end, right? So then let's hear the deloused video, and only to separate the sound of the guitar. See the separate sound of the acoustic guitar. So you can see that most of the background sounds have been suppressed. Now let's see some quantitative results. And we evaluated on visually aided audio source separation and visually aided audio delousing. And our method achieves large gains, and it also has the capability to match the separated source to meaningful acoustic object in the video. And please see the paper for details. And obviously, our system is not perfect. The most common failure mode by our method is when objects are incorrectly detected. And not all objects make sounds, and not all sounds are within the camera's view. So it will be important future work to explicitly model these cases. So this is an important topic, and has recently attracted many people's attention in the vision community. And here are some very interesting works that also study audio-visual source separation, and most of them focus on speech. Different from them, and we study a broader set of object-level sounds, including instruments, animals, and vehicles. And moreover, our method's training data requirements are distinctly more flexible. We are the first to learn from uncurated, in the wild videos that contain multiple objects making multiple sounds. So in conclusion, we have proposed a method to learn object sound models from unlabeled videos to perform audio-visual source separation. In future, we would like to integrate localized object detections and motion to further improve the separation results. And welcome to poster 1 for more discussions, and thank you so much for listening.
Thanks, Ruohan. So, do we have any questions? While people are finding microphones, I'll go ahead and ask maybe the obvious question. GANs, right? In your paper, you say, well, we're different from using a GAN because we don't set out to synthesize audio. But your results are amazing, and the separation is pretty clean, but it could be even cleaner, right? If we get rid of that dog, in the violin sequence. Maybe why not try a GAN here to help isolate which bases should be down-weighted or up-weighted?
Right. That's a great suggestion. Yeah, we haven't tried GANs specifically, But yeah, in terms of generation tasks like a spectrogram, so we are trying to predict, so like even if we are generating spectrogram, audio spectrum, we are trying to generate exactly the values in the spectrogram. So again, might get good quality results, but when we invert them to audio, it might sound not very perceptually true or real. Yeah, yeah, but yeah, definitely will be interesting work to try. Yeah, thanks.
Okay. Questions from the audience? I get to ask my other question then. For one-off events, so if we think of, well, the sound here is kind of being texture, what about sounds that are sort of, objects hitting each other or, kind of taps or bangs, things that aren't really captured using basis functions?
Right. That's a good question. So yeah, I think currently we are trying to model object-level sounds, trying to recognize the appearance of objects and trying to retrieve their characteristic basis and to then separate the sound. But in order to separate the interactions of different objects, probably I would say as future work, motion should be included, and in order to model how they interact with each other and to how the sound will change when they interact with each other.
So tracking information or
yeah.
flow.
Right. Yeah.
Great. Okay. Please see the author afterwards if you have further questions. Let's thank him one more time.